As always, pleasure to be here. They say that the best form of flattery is imitation, and after the gathering 4 years ago, I went back into a conference in the UK, which was dreadful. And so I've actually started, I've piggybacked on the work of Matt Parker in generating a monthly meeting called Maths Jam, where they meet in pubs and just basically jam with maths. And we have an annual meeting called the Maths Jam. Sometimes there's actual jam, but basically like musicians get together and just have fun, riff off each other, let their creativity go and share. So that's what we do with mathematics at the Maths Jam. And we've tried to model it after this. Plenary sessions, short talks. Last time we had 54 talks in 24 hours, not the full span. We let people go to bed in the middle. Some didn't. But anyway, I'm associated with 3 different organizations that are listed here. Denbridge Marine Limited is a company that tries to stop this from happening. This has a technical name. This is called a bad thing. And so we try and stop that. Kiel University I'm associated with. It's not Kiel in Germany or on Europe. It's Kiel in the middle of the UK. Not many people know where it is, so pub trivia, it's there. And these are, I do have to admit, these are particularly nice pictures of Kiel. But anyway, that's Kiel University. And so Solipsis Limited, which is what it has on my badge, through which I go out and do around about 150 or 160 talks every year. About half of them are on juggling, and I have here a map of the talks, both spread in space and time of the talks. This is slightly old. I've actually got another 15 talks that should be on there, but the ones at the left-hand side have already gone. But today I'm going to talk about mutilated chessboard. I love revisiting old problems and taking them further. And I do a workshop called Maths in a Twist, where you think, well, that's going to be the Möbius strip, and yeah, that's the first 5 minutes of a 50-minute workshop. And I go and I visit some of the things that Martin Gardner did in that, and then start to talk about classifications of surfaces and where the mathematics goes from there. So I'm going to revisit the mutilated chessboard, which you will all know, so I'm going to start with something completely different. If you take an ordinary deck of cards, shuffled or stacked or counted or whatever you do, and deal it out into piles of 4, can you select a straight 13 cards of all ranks, 1 from each pile? The way I've been presenting it when we've been here and we've been talking about this, can you choose the card on the top of each pile to make all of the ranks different? If you just deal them out randomly, then you may get duplicated ranks on the top. You may have 2 4s, you may have 7 7s. Well, that would be difficult. You may have duplicated cards. So can you choose the card that goes on to make them all different? And if you don't like the rest of the talk, you can think about that while I'm talking about the rest of it. You try and do it and it works the first time. And you ask yourself, what could possibly go wrong, to quote Jeremy Clarkson from Top Gear, which some of you will know and some of you won't. So anyway, look, if you don't know it, ask people around you. So anyway, mutilated chessboard. You'll all know this one. Take a chessboard, tile it with dominoes, and it's really easy. If you cut off one corner, you can't do it because it would require 31.5 dominoes. If you chop off adjacent corners, you can do it really easily. If you chop off opposite corners, then you can't do it. And we know that. By the way, I love this picture because it just drives chess people wild because it's the wrong way around. So anyway, if you try and tile this, you'll find that it doesn't work. And every time you try it, you find that you end up with 2 squares left over, which are the same color as each other. So you can't cover them with a domino. And there's the clue. You need to have the same number of black and white. If you chop off opposite corners, you've chopped out 2 of the same color. So it's clear that in order to tile it, it is necessary that the number of blacks and whites are the same. And most people stop there. Not everybody. I mean, ordinary people stop there. Normal people stop there. Mathematicians don't stop there. Puzzlers don't stop there because they're not normal people. And so you ask now, can I remove any black and any white and have it coverable? And the beautiful result, which some of you will know, Martin himself wrote about this, but the answer is yes. And there's a gorgeous, elegant argument that shows that on any even-sized chessboard, if you remove a black and a white, then it will be tileable. And I think that's a beautiful result. I'm going specifically to the 8x8 chessboard. If you remove 2 black and 2 white, is it necessarily tileable? I'm seeing lots of people go, no. Okay, let's leave it connected. Is it tileable? Because you could have isolated a corner. And the answer turns out to be yes. And the argument is neither elegant nor clean nor concise And there is space to say, actually, I may have got it wrong, because it's a horrible thing. So now let's cut out 3 black and 3 whites. And there is, in fact, a simple construction to show that this is not always possible. And I leave it as an exercise for the interested reader to find a configuration. So it is necessary but not sufficient to have the same number of black and white. So, so what is a sufficient condition? How do we know that something can't be tileable? Can we find when it fails a condition and therefore it cannot be covered? And so we can ask that. What is a sufficient condition to be able to cover the mutilated chessboard? And it turns out there is a beautiful and elegant and simple argument which relies on a simple piece of mathematics, beautiful, elegant, simple piece of mathematics from the early 1900s that turns out to be the same piece of math that proves that drawing a straight from 13 equal-sized piles is always possible. It's this connection that makes me do a little happy dance. And if you want to know more about that, come and talk to me or contact me afterwards. Thank you very much.